Today we're going to do the final lecture of Chapter 22, covering sections 8 and 9. We're talking about what would happen to a charged particle in an external electric field. Okay, so if you remember, the equation that we had for electric field was some force, was the force over a positive test charge. If you have an external electric field, the electrostatic force acting on a charged particle located in the external electric field, E, has the direction of E if the charge Q of the particle is positive, and has an opposite direction if Q is negative. So if we had some external electric field, just equally distributed like so, and then you have some charge with some positive charge down here. The force on that particle is going to be with the electric field, so the force would be in this direction. Now, if I had the same field, and this time I have a negative charge, the force is going to be in the opposite direction, the force due to the electric field. So when a charged particle of charge Q is in the electric field set up by other stationary or slowly moving charges, an electrostatic force F acts on the charged particle as given by the above equation. So we just rearranged this equation here. Now we have some external electric field. There's an actual charge, not just a test charge, but an actual charge that could be positive or negative there, and that's going to be equal to the force. All right, just a couple examples to go over. So Millikan did an oil drop experiment where he was able to calculate what the elementary charge was. And he did this by, inside of a cylinder, spraying just a little bit of oil into very fine particles. And the oil fell down through the tube and reached terminal velocity. Terminal velocity is when the gravitational force is equal to the drag force getting pushed up. So it ends up going at a constant speed. So the particle reaches terminal velocity, falls down through this slit here, and then reaches into, goes into chamber C. And in chamber C, you can either turn on or off these two plates of charge, and they were able to control the electric field inside of it. So if you had a charged oil drop and you turned on the electric field, they were actually able to set it so that the particle came to a complete stop. So basically it was suspended in air. Gravity was pulling it down, the electric field was pushing it back up. And since they knew that, they knew how much how strong the electric field was that they were putting in, they were able to calculate what the charge of the particle was. And they found out that by doing so, every charge was basically a multiple of some number. And they called this the elementary charge. So the charge of one single proton or one single electron. Now the second example over here is talking about inkjet printing. So the way inkjet printing works is there's some generator G. It shoots out a particle of ink. It goes through a charging unit, C, and then it goes through this deflecting plate where an electric field or an external electric field is created. While it's in the plate, depending on the charge that it was given, is going to dictate which direction it's going to go. So if it was given a positive charge, you would expect a deflection in this direction because it's going to go with the electric field. If you had a negative charge, you're going to expect it to go in the opposite, as it's shown here. And if you had a neutral charge, it would just go straight through. We would expect it to go through like this. Okay, so let's do an example. The figure shows the deflecting plates of an inkjet printer with superimposed coordinate axes, an ink drop with a mass of m is equal to 1.3 times 10 to the negative 10 kilograms, and a negative charge of q is equal to 1.5 times 10 to the negative 13 coulombs, enters the region between the plates. So here's our charge. The particle is initially moving along the x-axis with a speed of 18 meters a second. So its Vx is going to be 18 meters a second. The length of each plate is 1.6 centimeters, so the length is going to be 0.016 meters. Now the plates are charged and thus they produce an electric field. So you see that the electric field is pointing down in this case. So assuming that the electric field E is downward directed and is uniform and has a magnitude of 1.4 times 10 to the 6th newtons per coulomb. So that's our E value. What is the vertical deflection of the drop at the far edge of the plates? The gravitational force on the drop is small relative to the electrostatic force acting on the drop and can be neglected. So we're not going to worry about the force due to gravity in this case. All right, so we know that the drop's negatively charged and the electric field is directed downwards. Therefore, we would expect the drop to deflect upward, as is shown here. Thus, as the drop travels parallel to the x-axis at a constant speed, vx, it accelerates upward with some constant acceleration, ay. So it's going to have an acceleration in the y direction, constant speed in the x direction, so there's no acceleration in the x direction. This is just sort of like a kinematics problem from mechanics. So the first thing that we want to do is take Newton's second law, F is equal to ma, for the components along the y-axis. So our acceleration in the y-axis is going to be F over m, which is the force over the mass. In the previous slide, we saw that the force is equal to QE, which is the charge times the electric field, divided by m. So that's going to be our first result. All right. And we're going to let time t is equal to the time for the drop to pass through the plates. All right. Now we can use kinematic equations to find, well, how long is that going to be? So in the y direction, our kinematic equation is going to be delta y is equal to v naught in the y direction plus 1/2 acceleration in the y direction, t squared. In the x direction, we have the same equation. So you have delta x is equal to v naught in the x direction times t plus 1/2 at squared. But we know it's not accelerating in the x direction, so we'll just leave it at that. The second term is just going to cancel out. Okay, so our y value is going to be just 1/2 acceleration in the y direction t squared. The initial velocity in the y direction is 0, so this first term is just going to cancel out to 0. And then our x, so the change in x is going to be the full distance of the plate. So you're starting from here, you're going all the way to the end of the plate, and that's going to be our distance L, so our change in x is just L. And that is going to be equal to Vx, which was given to us, times t. All right, so now I have two equations with t in it. What I'd like to do is get rid of the t now. So if I solve the x equation for t, it's going to be L over Vx. I take this result and I plug it into here. I also take our QE over m, plug it in for a, and the result that we get is y is equal to QE times L squared divided by 2 times the mass times the x component of the velocity squared. I'm going to go ahead and take that resultant onto the next page. So just to rewrite, we have y is equal to, QE L squared divided by 2m Vx squared. We can go ahead and plug in everything. So our Q was 1.5 times 10 to the negative 13 coulombs times 1.4 times 10 to the 6th newtons over coulombs times 1.6 times 10 to the negative 2 meters, which is our distance, squared, all divided by 2, times our mass, which is 1.3 times 10 to the negative 10 kilograms, times our speed in the x direction squared, which is 18 meters a second squared. Plugging that into our calculator, we find that the y displacement is 6.4 times 10 to the negative 4 meters. And that is our result. Okay. Well, what if we had an electric dipole in an external electric field? So with an electric dipole, when an electric dipole is placed in a region where there is an external electric field, E, electrostatic forces act on the charged ends of the dipole. If the electric field is uniform, those forces act in opposite directions but with the same magnitude. So the force is just going to be QE, but depending on the charge, it's going to depend on where the direction of the force. So if you look in our chart over here, in our image, we have that the positive charge is going to go along with the electric field, the negative charge is going to go against the electric field. So although the net force on the dipole from the field is 0, the center of mass of the dipole does not move. So this is our center of mass right here. That's going to stay the same. The forces on the charged ends do produce a net torque on the dipole about its center. So it's sort of rotating around. It's going to kind of rotate in this direction, in this case in the clockwise direction. So the center of mass lies on a line connecting the charged ends at some distance x from one end and some distance d minus x from the other end. So if I wanted to find the torque, and just a reminder, our torque equation is Fd sine theta. It's going to be all the torques added together. So it's going to be torque from one of the particles plus the torque from the other particle. So you have Fx, and x is the distance away, times sine theta, plus F times d minus x, because depending on the size of the charges, it might not necessarily be in the center. So we're going to use d minus x and not just x. But when you write it like this, you actually see that this fx is going to cancel out, right? And then all you're going to be left with is fd sine theta. Well, Fd is also equal to our dipole moment times E sine theta. So the equation that we get for the torque is just going to be the cross product of our dipole moment P crossed with our electric field E. Now, if you remember, our dipole moment is going to be from the negative charge to the positive charge. So that's why you have our dipole moment written here in that direction. Now, if you look at the direction of our electric field with that, you see that this is the electric field, and this is our dipole moment. So if you do the cross product, you're going to use the right hand rule. You put your fingers towards the dipole moment, curl them around to E. Therefore, the direction of the torque is going to be going into the page, and that's shown by our X right there. Okay. So potential energy can also be associated with the orientation of an electric dipole in an electric field. So the dipole has its least potential energy when it is in its equilibrium orientation. So equilibrium orientation would be something like this. You have both charges are along the same line. You have your negative and your positive, and it's oriented like that. All right, this is going to be the center of mass. And that would be equilibrium. So the expression for the potential energy of an electric dipole is in an external electric field is simplest if we choose the potential energy to be 0 when the angle theta is 90. All right, so U is going to be 0 when theta is 90 degrees. So this is our angle theta right here. If we had an orientation like this between the dipole and the electric field, that is when the potential energy is going to be 0. So the potential energy U of the dipole at any other value of theta can be found by calculating the work done by the field on the dipole when the dipole is rotated to that value of theta from 90 degrees. All right, so it's showing you that our potential energy U is just going to equal to the opposite of work. And we can find that with the integration of torque. So you have negative times the integral from 90 degrees to some angle theta, right? Because you're starting at 90, you're going to some other angle, and then you have torque d theta. Well, we know the torque is the dipole moment times the electric field, sine theta, d theta. So taking the integral of sine theta, you're going to get cosine theta. So your end result is negative P, which is the dipole moment, times the electric field, times cosine of theta. Right, so this is our potential energy. And that's shown down here. It's actually as a dot product, since it's cosine. So U, which is our potential energy, is equal to the opposite of our dipole moment times the electric field. Okay. So let's go and do an example. A neutral water molecule, H2O, in its vapor state has an electric dipole moment of magnitude 6.2 times 10 to the negative 3 coulombs times meters. How far apart are the molecules centers of positive and negative charge? All right, so let's draw a picture so we know what we're talking about here. So let's say we have our oxygen atom. It's going to be O. And then we have 2 hydrogen atoms, and this is how they're generally oriented, or how we draw them. This is going to be hydrogen, and this is going to be hydrogen. Now, because of this arrangement, the molecule ends up having slightly one side that's slightly more negative and one side that's slightly more positive. So we'll use this delta D, or excuse me, delta positive. So the hydrogen sides are going to be slightly more positive. The oxygen side is slightly more negative, and what that creates is a dipole moment, P, somewhere near the middle of the atom, or the molecule, excuse me. All right, so it's going from the slightly more negative side to the slightly more positive side. And what we're trying to find is the distance between, we'll say distance D, the distance between the more positive side and the more negative side, or the center of the negative. Okay. So a molecule's dipole moment depends on the magnitude Q of the molecule's positive or negative charge and the charge separation D. So there's 10 electrons and 10 protons in a neutral water molecule. So the magnitude of its dipole moment is just going to be, so our dipole moment, just the magnitude is going to be Q times D. That's going to be 10 times E, because that's the charge of 10 electrons or 10 protons, and then some distance D separation away. Okay, so if I want to solve for D, see what this D is. It's going to be equal to our dipole moment divided by 10E. Our dipole moment is given as 6.2 times 10 to the negative 30 coulombs times meters, divided by 10 times 1.60 times 10 to the negative 19 coulombs, which is our elementary charge. We find out that the distance ends up being 3.9 times 10 to the negative 12 meters. Okay, so part B is asking us if the molecule is placed in an external electric field of 1.5 times 10 to the 4th newtons per coulomb, what maximum torque can the field exert on it? So such a field can easily be set up in the lab. So the maximum torque is going to occur when the angle is 90 degrees, when you have a 90-degree angle between the electric field and the dipole moment. So our torque, this is part B, our torque is equal to the equation that we had earlier, which is PE cosine of theta, oops, excuse me, sine. We can just go ahead and plug things in. So we have our dipole moment, which is 6.2 times 10 to the negative 30 Coulomb meters, times our electric field. The external electric field is 1.5 times 10 to the 4th newtons per Coulomb, sine of 90. Now sine of 90 is just going to be 1, because that maximizes the equation. Oops. This is just going to be 1, so I don't have to worry about that. Alright, so our torque then is going to be equal to 9.3 times 10 to the negative 26 Newton meters. Okay, and that's our result. Alright, on the next page it just shows you the work that I just gave. So we took our equation, plugged in our values, used sine of 90 because that's going to maximize it, and the other angle is just going to cause this value to be smaller, and then we have our final result. So part C is how much work must an external agent do to rotate this molecule by 180 degrees in this field, starting from its fully aligned position for which theta is equal to 0. All right, so let's look at this. Let me move my head again. All right, so for part C, our current orientation is we have a negative charge over here, positive over here. Our electric field is going in this direction, and this is also the direction of our dipole moment. We want to rotate it all the way around, so 180 degrees, so that these switch. So our end result is going to have some positive over here, and then the negative charge on the other side. And so I'm basically flipping the dipole moment. Okay, so the work done by an external agent by means of a torque applied to the molecule is equal to the change in the molecule's potential energy due to the change in orientation. All right, so our work is just going to be equal to the change in U, or the change in potential energy, okay, which is going to be equal to U of 180 degrees, because that's where we're going to end up, minus the potential energy at 0 degrees, because that's where we start. Okay. Plugging things in from here, we use the same equation. So for our U, we have negative dipole moment times E cosine of 180 minus negative dipole moment times E cosine of 0. Okay, oops. This last value here is 0. Okay, so cosine of 0 is just going to be 1, so that's not going to change anything. Cosine of 180 is going to be negative 1, so that's going to change the sign of our first part. So you have PE here, and you're going to have a PE here, because negative and negative. So our work is just equal to 2 times the dipole moment times the electric field. All right, now that it's simplified, we can just go ahead and plug in values. So our work is equal to 2 times, our dipole moment, which is 6.2 times 10 to the negative 30 Coulomb meters, multiplied by 1.5 times 10 to the 4th newtons per Coulomb. And plugging it into our calculator, we get 1.9 times 10 to the negative 25 joules. Okay, that's it for this chapter on electric fields.